good morning, everybody. Hopefully having fun so far, and you've survived the mic session, which is always good. Okay. Come take a sec. So the track we have today is our Tessent track, which is both for test and our embedded analytics products. So hopefully we have a range of different topics covered by a number of customers today that will be of interest. Alongside the presentations that you'll receive today, I'd also recommend going and checking out our usability labs. So opportunity to get kind of direct hands-on experience with the tools. So they're proving extremely popular. So pop over to the usability labs. There's plenty of people over there to kind of guide you through what's going on and kind of get hands-on. We also have our Ask the Expert area. So we've got a demo session over there. So feel free to go and kind of talk to the folk over there. We have a hardware demonstrator of our embedded analytics products. Plus, we've also got a good number of our Tessent DFT folk kicking around, so a lot of them in the room. So I don't know if it's worth just all the Tessent folk just quickly stand up so you know who to go and grab if you have any test-related questions. So feel free to grab any of those guys over at coffee and explain your requirements and problems to them. So they'll be able to help you out. Okay, so let's get started. So the first session, gone wrong already. So to kick off this track today, so first off, it's me. So I'm going to give you an insight into what we're seeing in the industry, what we're hearing from our customers, what products we have either already today out in the field and in development to kind of address those challenges, and also talk a little bit about kind of what we're doing in the area of AI to kind of make those tools more efficient and more optimized. So if I go to here, okay, what I am going to do is give that to Chris. He can keep me under control. Okay. So the grand challenges of test. So there's a number of areas I think we're seeing in the industry when we talk to all our customers and we see what's going on. For you guys from a DFT perspective, life's not getting any easier. There's new challenges coming, and if we look at kind of what those challenges are and how they kind of spread, first off, obviously a big one for everybody is technology. So obviously we're seeing leading edge technologies. We're seeing 3 nanometer down to 2 nanometer, and the impact of that is absolutely huge. So we've now got manufacturing processes with kind of 1,000 steps per wafer. We've got all the new types of transistors. We've got gate all around becoming quite prolific. We've got a lot of concern right now about aging. So we all know silicon degrades over time, but with these new processes, it's becoming more and more relevant to what we're seeing. And we're seeing a lot more reports of what we would call silent data corruption. So for anybody in the room that hasn't been exposed to silent data corruption, these are the defects that are not picked up during tests. Everything is passing. Everything is passing all the DFT tests. The system is working functionally, but every now and again, there's a little defect issue that causes the system to malfunction. And if we rerun all the tests, everything still looks fine. So So there's still potential defects that are occurring in silicon. I've only got 2 minutes left already. Yeah, so that's the pretense of silent data errors is we're seeing more and more of these issues in systems occurring that are not detectable through regular test. Oh. The next challenge is also, okay, we've got the technology, but also making the use of those technologies. We have the complexity of designs are growing. So not just on the single core, but as we increase the size of the designs, we're seeing kind of multi-corner, multi-die, and like here's just an example of recent design, 92 billion transistors. So this was an Apple design that was published recently. So in terms of challenges for designs, it's getting quite challenging. So not only do you have to deal with all of the new potential faults and defects, you're doing that in a more complex environment. And then there's a lot of focus on, we're very used to dealing at the silicon level, the device level, but actually there's a lot more focus now at a system level. And here's a chart that actually we were given permission to use from Tesla, which kind of shows how the sizes and complexity of systems are scaling over the years as well. So, and because of that, like I say, there's a number of new areas we need to focus on in the test domain. So, lifecycle management is key. Security is becoming increasingly important, and then the whole challenge around reliability, aging, functional safety. So we're in a world now where we're not just running test patterns and testing silicon. There's a whole range of things that we have to consider. If we look at some examples, data centers are always a good example because they're really leveraging the maximum complexity they can achieve and all the leading edge technology nodes. And you're seeing, as we're becoming more and more reliant on cloud-based services, software as a service, the reliability of these data centers is becoming critical to our daily lives. And as you know, if social media drops out, if WhatsApp disappears for a day or Facebook drops out for a day, it's quite a critical event. So in terms of what these customers are looking for is the reliability factor, and also the whole aging concept as well. So we're all becoming very eco-friendly. We're all looking at the environment, and if in terms of the silicon that are going into these data centers, they have a kind of a well-defined life cycle. If through our technology we can extend that life cycle, say from 4 years to 6 years or 6 years to 8 years, the return on investment for silicon users is absolutely huge. So going back just quickly to the silent data errors or silent data corruption. So what are we really looking at? And it's not a new problem. It's just becoming more observed. So you're all hopefully familiar with the typical bathtub curve, where you have your early life failures, and then you have the failures as the silicon reaches kind of the end of its life. But we're really putting a lot of effort in to address that upfront early life failure. So we, with the new technologies, we're really focused on new fault models. So we already have quite an extensive range of advanced fault models to really address the advanced nodes, but also now looking at new fault models to stress the devices to really weed out those early life failures. So hopefully within the next year or so, we should be starting to see some results from those technologies. So if we look at the whole Tessent portfolio, we believe we have pretty good coverage of the whole silicon lifecycle area. Everything from, we have our test insertion, so inserting all of the test IP at the early stage of your design. The pattern generation, so generating those high quality test patterns that I talked about to address all of the new challenges we're seeing in terms of silent data errors. And when we do see defects and errors in the silicon, we have the yield learning and the diagnosis capabilities, and also looking at not just debugging faults and defects from a structural test perspective, but also using the structural technology to help with your functional debug. So looking at moving away from, or in addition to silicon diagnosis of structural patterns, but also using the same structures to be able to do scan dump. So being able to, when you see an issue with your device running functionally, we're able to stop the device and scan out the functional data so you can start to debug your functional operation. System level tests, so moving, not only testing in the fab at the ATE level, but also moving into the system space, being able to test your silicon within part of the system. And then obviously, depending on the application of the device, starting to look at safety, security. So automotive, there's a whole ton of safety requirements. And then being able to run those kind of in-system as part of a functional operation. And then going over and above, we have our embedded analytics technology, which is looking at functional monitoring. So monitoring the functional operation of the device when it's running in its normal operational mode. So you can see in terms of a product portfolio, we have a very broad portfolio of technologies now to really cover every aspect of your test, your bring up, and life cycle monitoring for your whole silicon life. And if we dig down into some of the key technologies that help deliver that, the one that probably everybody in the room, or hopefully everybody in the room, has heard about already is our SSN technology. So this is our flagship ATPG platform, being able to deliver your ATPG content in a packetized form on a hierarchical design. And the concept of that is, instead of direct access test through functional pins, we have a dedicated test bus, our SSN bus, where we packetize the data, we deliver the data over the bus, and then that data is delivered and decoded at the core level. So only the core that the data is relevant to gets that particular data packet. So it really does optimize the ATPG process in terms of data volume, performance, and also complexity. So those of you who've done large hierarchical ATPG implementations in the past, you're aware there's a reasonable amount of complexity once you do the top level integration SSN really does remove a lot of that top level complexity, because we're now we're running on a bus-based implementation to really improve that overall architecture and make it a lot more scalable. And as I said, we're also looking at leveraging the this advanced ATPG architecture to help you with your functional debug. So really enabling you to run your design in a functional mode, and then when you run into a functional issue, we can then halt the operation of the device, and then use our SSN technology to effectively dump out key pieces of the design data, the functional data, to help you debug that. And it's worth noting there's actually there's a new IEEE standard that's forming at the moment, P2929, which is all based around the scan dump technology. So everything we're putting together is going to be 2929 compliant. So it will provide an extremely useful debug capability within your functional design. And then again, looking at the level of complexity that we have in these large designs, IJTAG for at least 10, 15 years has been our cornerstone of device setup, configuration. All of our technology is IEEE 1687 IJTAG compliant. But again, as the designs get larger and larger and larger, we see some restrictions with IJTAG in terms of speed and complexity. So where at the moment we're configuring all of our test IP with IJTAG, we're looking at moving basically the deployment of the IJTAG data to be done over the SSN bus. So we're really moving the configuration data from a very slow serial interface and applying that data over the fast parallel bus that we're implementing with SSN to remove some of those restrictions with IJTAG. So really moving towards high bandwidth IJTAG via the SSN. So again, a very similar technology where we packetize that configuration data up, we deliver it down that high speed bus, and then at the core level, we're pulling that data off and decoding it for the various blocks. And also, I talked a little bit about monitoring. So we're increasing our portfolio of monitoring technology. So from functional monitors and looking at other monitoring technologies, because monitoring the various aspects of the silicon during test, during functional mode, is becoming more and more critical on a daily basis to keep track of the overall health of the device throughout its life cycle. So again, leveraging our standard SSN bus technology to be able to collect that data from the various monitors that we're embedding on chip. And it's not just at a die level. We're seeing a lot of new devices coming along where they're becoming 2.5D, 3D devices. So we've got a couple of presentations today from customers that are starting to working that way. So all of our technology based around the SSN infrastructure is very expandable and very compatible with the IEEE 1838 standard, which defines the setup and configuration of multi-die devices. So in terms of kind of moving from a single die implementation to a multi-die implementation, all of your test infrastructure and your methodology doesn't have to change too much to move from single die to multi-die, because SSN is still very critical to the overall implementation. And then we have support for the additional IP that's required for 1838. And then at the I/O level, again, there's always a challenge to get the data on and off chip as fast as possible. So integration with kind of high-speed I/O to speed up that delivery of the test data. So not just using your general GPIO pins to get test data on and off chip, but also to use the high-speed I/O. And then I talked a little bit earlier about SLT. So again, everybody's familiar with testing at the ATE level, but also at the system level, because system level testing is becoming more and more critical. Being able, again, to use the same infrastructure, but starting to use your functional interfaces and different types of tester to deliver things at the more of the system level. So a whole range of technologies you see there in place to address the challenges that we see. And when we talk about AI, so AI is an interesting up and coming topic. So actually within the Tessent product portfolio, AI has been around for the best part of 12 years now. So we started to look at AI in terms of our silicon diagnosis products. So with our silicon diagnosis products, you'll start to diagnose your defects at a die by die level, and essentially you start to get a whole bunch of different defects per die. And what we can do and what we do with our diagnosis and yield learning products is really use AI ML and the knowledge that we have about those failures to really narrow down the root cause of those defects and start to look at kind of what the actual the one or two root causes for those issues are. And if you look at how we do that, so we start off by collecting a lot of failure data through our scan diagnosis tool. And for a particular example, for a whole range of different failing die and different types of failures, we can potentially kind of narrow things down to a very small number of kind of potential defects, potential root causes. We then pull the volume data from a large wafer lot, and then what we see that the different root causes have kind of very different profiles within those that collection of data that we pull, and then we can model the probability of those small number of root causes being the cause of the failures on those die. And then the smart bit comes in that we're using AI algorithms to really kind of identify out of all of the failing data which root cause those failures fall into. So I think this may have so if you look at the way our AI/ML algorithm is working, it's really analyzing the data and grouping the failure information into the three different areas or the three different potential root causes, and using AI/ML, we're able to really reduce the noise around the failure data that we see and narrow down onto the actual root causes itself. And in terms of results, using this kind of technique, we see huge gains in terms of diagnosis resolution, PFA performance, and chain diagnosis resolution. So I know this is just a one example of where we're using AI ML within the Tessent portfolio, but what you'll see over the coming years is this kind of technology extended into the full product portfolio, because the full product portfolio has enough configurability, enough flexibility to really take advantage of AI ML to optimize and enhance the performance of what you're doing. So in terms of challenges, so SSN is, as I say, is really the cornerstone of our technology. So we've got all of our ATPG, memory BIST, and RTL level integration. We've got full support there now for multi-die technologies, and really focused on the system level test, in-system SLT, going forwards, as we're seeing a lot of demand to really support the system level side of things. So hopefully that kind of gives a very brief kind of overview of what we're seeing in the industry, what we're doing within the Tessent, and where we're heading to in the future. So with that, what we're going to do is we'll move on to the customer presentations today. So dig into the more detail, some of those technologies and how you guys are using them in the real world. So